This is a problem on page 13 of your distance learning packet, and I'm going to perform the problem on the board in a moment. A thin film of kerosene whose index of refraction is 1.501 floats on a puddle of water whose index of refraction is 1.333. White light from the sun falls almost perpendicularly on the film and appears magenta due to the elimination of green light, whose wavelength in a vacuum is 575 nanometers. What is the minimum thickness of the film? And I would like to reiterate, we want to know the minimum thickness of the film for which green light is destroyed through destructive interference. White light falls nearly perpendicularly on the film, but the conditions of the film, the thickness, allow green light to be destructively interfered with and eliminated to the viewer. So we have light hitting the top surface. Some of that light reflects, some of it is transmitted. The reflected portion I'm calling ray 1. Of the portion that is transmitted into the kerosene, some of it goes into the water. I am not interested in that component of the light. I'm interested in that component of the light that reflects off the bottom kerosene water interface, and after leaving the kerosene film is visible or not to a viewer looking at this portion of the kerosene. Like if you're looking at the kerosene, you don't see any green because of destructive interference. Now, the conditions for destructive interference are that the extra distance traveled by the light that enters in the kerosene and reflects off of the water, so-called ray 2, the extra distance traveled by it is 2t. Down t, up t, together is 2t. I'm going to worry about phase shift if it is something to worry about. Now, I only worry about a phase shift if one of the waves flips and the other doesn't. If they both flip, I don't worry about it. It's as if they both flipped, and so there's no change in their relative orientations to each other. Now, ray 1 was traveling in air whose index is 1, and it reflected off of a higher index of refraction, a media with a higher index of refraction. Ray 1 flips. Ray 2, however, was traveling in kerosene, 1.501 index, and it reflects off of a lower index of refraction media. It does not flip. Because one of them flips and the other doesn't, I need to account for that extra, essentially as if one of them traveled an extra half wavelength. And I want destructive interference to result. Now, the conditions for destructive interference are that these two rays are off by a half wavelength, or 1.5, or 2.5. As long as it's an odd integer multiple of a half, we have the conditions for destructive interference. Okay, I'm going to subtract a half from both sides. When I do, this becomes 0, this becomes 2 halves, this becomes 5 halves minus a half is 4 halves, 7 halves minus a half is 6 halves, and just restating that, that means 2t equals 0 wavelengths, 2 over 2, which is 1 wavelength, 4 over 2, which is 2 wavelengths, etc. Dividing by 2 to get the single thickness that I'm interested in, I get 0 over 2, wavelength over 2, 2 over 2, 3 over 2, etc. Now I'm just going to rewrite those as this is the minimum thickness that gives me destructive interference for green light. Last but not least, though, before I take the wavelength that was given, in the problem it was given to be 575
nanometers.
I need to calculate the wavelength in the kerosene. The wavelength in the kerosene is the wavelength in vacuum divided by the N of the kerosene. For this problem, those values are wavelength in the kerosene is going to be 575 nanometers divided by 1.501, the index of refraction of the film that the extra path travel was in. 575 divided by 1.05 equals 383. And now I can divide that by 2. And I get 192 nanometers as the minimum thickness of the kerosene that leads to the destructive interference and elimination of this green light in vacuum.